Hello and welcome to College Algebra 2.7 Inverse Functions. So today we're going to find and verify inverses, graphs of inverse functions, and talk about what it means to be one-to-one. So what are inverse functions? They kind of undo each other. So we've talked about f of x, so this is the x coordinate being replaced with a number. This over here represents the y coordinate. So this has the coordinate 2, 8 inside function f, where here this would be the opposite, 8, 2. So inverses, the domain and the range will swap. So we see that my x became my y, and my y became my x there. So often they'll have opposite interactions like +6 and -6, or ×2 and divide by 2, square root versus squared. This just means the inverse of f, where f of x is a function. The inverse is to the power of -1. So how do you verify two things are inverses? You can do either fog, you should do fog and goff, and it simplifies down to just x. So for example, if I'm doing fog and I'm taking the entire g function and I'm plugging it in for x in the f function, we get 2 times the quantity of x over 2 minus 2.5 plus 5. I can distribute the 2, so I get 2x over 2 minus 5 plus 5. That simplifies out, and 2x divided by 2 gives me just x, so I'm all good. The logic would hold in the other direction, so 2x plus 5 over 2 minus 2.5. We can write this as 2x over 2 plus 5 over 2 minus 2.5. 5 over 2 is the same thing as positive 2.5. So those cancel out. 2 divided by 2 cancels out, and I'm left with just x as well. The other way you can find inverses, which we're going to talk about here in a second, is this. If we agree that conceptually speaking, this is the same thing as y, and as I just told you, the x's and y's get swapped, then I can swap the location of x's and y's. So x equals 2y plus 5. And I can solve for y. So minus 5, divide by 2. We get x over 2 minus 2.5 equals y, which is exactly g of x. So because my f of x inverse is g of x, I should check if my g of x function is f of x. So either way, we can verify inverses, either through fog or finding both inverses manually. Here's just another example, excuse me, of finding fog or goff. So you can pause and take a look at that. But because I got exactly x in both, they are inverses. So here's just talking about finding that inverse idea. If you don't have it, or if you don't have a second equation, you would have to first swap the x's and y's and solve for y. So here we would square both sides. X squared equals y plus 3 minus 3 minus 3. We get y equals x squared minus 3. Now, interestingly enough, this also needs a restriction. You would need to include the restriction of x has to be greater than or equal to 0. Because if I were to graph this function we have right here, y equals x squared minus 3, it would look something like this. And you would say that that domain would be all real numbers, and the range would be from -3 to infinity. But I told you earlier that domains and ranges have to switch. I even put it right there. My range and domain have to flip. So looking at my domain, that becomes my new range. That's perfectly fine. But this has to switch. And as we see, my domain currently says all real numbers. It needs to say 0 to infinity. So I know that x has to be greater than or equal to 0, effectively erasing this whole piece right here. The reason that happens is we'll talk about here in a second, but if I were to graph my original function, that would look something like this. These two graphs, the red one and the blue one, need to have the same shape. If it's a square, it doesn't have that same shape with that parabolic motion. Find the inverses, just flip-flop the letters, and solve for y. So add 3, divide by 4, divide by 4. We get y equals x plus 3 divided by 4. Same idea. Swap the letters. Minus 4, minus 4. Multiply by the reciprocal to get rid of a fraction. We get 5x over 2 minus 10 equals y. Graphs of functions, they are symmetric across this line. So I told you earlier with this one, so that would look something like this. It's a square root function. The plus 3 means moving over to the left 3, what we've talked about before. Now, if I were to graph this one in its normal state, it would look something to the effect of this. It's it's a parabola, but they're not the same shape. As we said earlier, we need this restriction, which will eliminate this branch, and therefore we get a very similar looking shape with those green and red. With that, we already understand that for every x value, there's only one y value. That's the definition of a function. Now, in order to be one-to-one, there is also only one y value. So we cannot repeat x values. No, repeat y values in order to be y-to-one. So what this tells us is if the inverse is a function or not. The vertical line test tells me if f of x is a function. So I would say f of x is a function right here. Yes, because it passes the vertical line test. But it doesn't and it also passes the horizontal line test. Horizontal line test would tell me if it's one-to-one. Why is this important? Well, if I flip back a slide here, we can recognize that these shapes are very similar and almost rotated in such a way that mathematicians got tired of seeing an equation here and then feeling like they had to copy and recreate it across that reflection line. So for example, if I were to draw a reflection line and create the inverse of this graph, it would look like this. Well, this original function passes the vertical line test, this blue one right here. The black wouldn't pass the vertical line test. And you can tell that immediately because the original graph fails the horizontal line test. It is not one-to-one. I repeat some y values. So instead of having to make an inverse every single time and do that vertical line test, the horizontal line test of the original accomplishes the same goal. Thank you for listening, and I hope you have a great